On the night of March 14th, 2024, storms crossed central Ohio, and Columbus sat inside a sky that was being watched by radar every few minutes. The sirens stopped before the answer was settled. Around the city, people searched the same practical thing, whether a tornado had actually happened. The number that mattered was not the loudest wind gust. It was 0 feet, the distance between a rotating column of air and the ground. A funnel above a city is not enough. A radar couplet above the rooftops is not enough. Surveyors would have to look for snapped trees, peeled roofs, and debris laid down in a pattern the storm could not fake by blowing straight through. That search began after the dangerous part had passed. The warning was over, but the event record was not finished. A tornado is proved by joining what the atmosphere showed in real time to what the ground kept afterward. The evidence is forensic, rotation on radar, converging damage on the surface, debris that points back toward a path, and a wind estimate drawn from what failed. A tornado has a strict definition. It is a rotating column of air connected to a cloud above it and in contact with the ground below it. That last part is the hard part. The bottom of the circulation can be wrapped in rain. It can pass through darkness. It can cross open ground without lifting anything obvious. The visible funnel is made of condensed water droplets, and it does not always reach the surface even when damaging rotation does. Meteorologists, therefore, do not prove a tornado only by seeing a funnel. They look for evidence that rotation reached the ground. The question after the warning is not whether the storm was dangerous. The question is whether the damage came from a rotating column in contact with the surface or from severe wind moving mostly in one direction. Doppler radar measures motion toward and away from the radar. When winds moving in opposite directions sit close together, the display can show a velocity couplet. That is strong evidence of rotation inside a storm. Some radars can also show a tornado debris signature. In that case, the radar is not just seeing wind. It is seeing lofted material with shapes and sizes unlike raindrops, in the same place as the rotation. Those signatures can be powerful evidence, but they are not perfect proof in every case. The radar beam rises with distance from the radar site. In many storms, it samples air hundreds or thousands of feet above the ground. A circulation can be clear aloft and weaker at the surface. The official record often depends on whether the damage below matches the rotation above. After the storm, survey teams work the damage path. They drive roads, walk properties when they can, record locations, photograph failures, and map the direction objects fell. Straight-line wind usually pushes damage in broadly the same direction. A tornado often leaves a convergent or rotational pattern. Trees may fall toward each other from opposite sides of the track. Wall debris may be thrown in a direction that does not match the larger storm motion. Fences, shingles, signs, and insulation can mark a narrow corridor rather than a broad swath. No single broken tree proves the case. Trees have weak trunks, shallow roots, and uneven exposure. Buildings fail at corners, garage doors, and roof edges before they fail as whole structures. The pattern is the evidence. A survey asks whether many separate objects, damaged in many separate places, point to the same rotating path. Urban tornadoes are especially difficult to confirm in real time. Buildings block sightlines. Rain and night hide the lower circulation. Wind is forced between streets and around towers, so even non-tornadic wind can turn sharply at ground level. The debris field is also more complicated. A roof membrane can travel farther than a brick. Glass can fall straight down while siding moves downwind. Air accelerated between buildings can damage one side of a block and leave the next side less affected. That is why surveyors do not treat one dramatic object as the answer. They compare roof damage with tree fall with radar timing, and radar timing with the mapped path. In a city, the proof usually comes from consistency across many imperfect clues. Once a tornado is confirmed, the rating is a separate step. The Enhanced Fujita scale does not usually measure the tornado's wind directly. It estimates wind speed from damage. The method uses damage indicators. A damage indicator can be a 1 or 2 family house, a manufactured home, a hardwood tree, a school building, a warehouse, a transmission tower, or another defined object. For each one, surveyors judge the degree of damage. Missing shingles means something different from a removed roof. A snapped softwood tree means something different from a well-built house swept from its foundation. The rating is therefore an estimate of wind capable of causing the observed damage, not a direct instrument reading in most cases. Construction quality matters. Exposure matters. A violent tornado crossing an empty field may leave little rated damage. A weaker tornado hitting vulnerable structures can look severe unless the survey accounts for how those structures were built. The final entry can change as evidence arrives. A first report may say possible tornado. A later survey may confirm a tornado, assign a path length and width, and give an enhanced Fujita rating. In other cases, the damage may be classified as straight-line wind if the pattern does not show ground-level rotation. This is why the answer after a siren is sometimes delayed. Radar tells meteorologists where to look. Reports from the public and emergency managers narrow the search. The ground survey decides whether the atmosphere left the signature required by the definition. For Columbus and for any city after a warning, proof is not a single image of a funnel. It is the match between rotation in the storm and rotation written into the damage below. What can remain open is the exact peak wind, the exact moment of ground contact, or the details of a path hidden by darkness, rain, or inaccessible property. Settling those would require closer observations, direct instruments in the path, clear video tied to location and time, or damage evidence that survives well enough to map. That's why source. If this was worth your time, like it, share it, and tell me in the comments what you want examined next. If you would like to support this work, the Patreon link is in the description.